Distinguishing between a human author and a machine generator is incredibly difficult. Zooming in, the patterns blend into a single, indistinguishable visual field. To pull these sources apart, the standard approach relies on zero-shot statistical metrics. One of the most common is entropy, which measures how predictable a sequence of text is to a language model. Another baseline metric is logrank. This tracks whether the text consistently relies on words that the model ranks highly in its probability distribution. These methods share a core assumption. They evaluate text by checking if it is highly probable, operating on the premise that AI-generated text is generally smoother and more fluent than human writing. This creates a specific vulnerability when adversarial attacks enter the picture. A user can easily apply a perturbation tool or ask an AI to paraphrase its own output to sound less robotic. Paraphrasing scrambles token-level statistics. It introduces less predictable word choices, which lowers logrank and raises entropy, causing traditional detectors to register false negatives. Current detectors fail because they measure raw statistical fluency. They evaluate the surface of the text rather than the underlying architectural conditions that produced it. To find a more resilient signal, we have to look inside the model's training pipeline. Modern language models are built in two distinct stages. The first stage is base pre-training. The model consumes open domain corpora and optimizes for unsupervised next token continuation, learning general linguistic regularities. The second stage is post-training. This typically involves supervised fine-tuning and preference-based optimization, like RLHF or DPO. Instruction tuning shifts the model's objective. It stops generating unsupervised continuations and starts generating conditional responses to specific user prompts and system instructions. This optimization leaves a trace. Because models are instruction-tuned, the text they generate is structurally optimized as a response, rather than a standalone document. Researchers call this latent dependency. Even after you copy the text and remove the original prompt, the generated words retain a statistical memory of being drafted under an assistant role. Reliable detection requires treating the text as a conditionally dependent artifact. A base model factorizes likelihood by looking only at preceding tokens, but instruction tuning introduces a global instruction, CG. Once prepended, it becomes part of the causal context, altering the probability of every following token. That CG variable represents the system prompt or user request, the directive that forces the model to behave as an intelligent assistant. During detection, we no longer have the original prompt, but the dependency might still exist. We can test this by artificially reactivating that CG variable. This is the mechanism behind EchoPrompt. The system takes an unknown passage and prepends a generic task-agnostic prefix, a phrase like, "You are a helpful AI assistant. Below is the content you generated." This specific phrasing provides a broad assistant response framing. It restores the coarse global condition without needing the exact details of the missing user request. By mathematically reintroducing a generic CG, we shift the evaluation. We stop looking at absolute probability and measure the text's conditional probability under an assistant framework. This chart shows the contextual gain when injecting the EchoPrompt prefix. For human writing, the likelihood shift is minimal, virtually zero gain. But machine-generated text reacts differently. Applying the exact same prefix triggers a massive upward spike. The AI text snaps into alignment. Its latent structure naturally fits the restored assistant condition, yielding a much higher probability score than it previously had. Human text fails to spike because it was never structurally optimized to exist downstream of a system prompt. It lacks that built-in dependency. However, measuring this conditional probability alone is risky. Intrinsic fluency, high-frequency phrases, and common words can all inflate token probabilities, mimicking a true contextual reaction. We have to isolate the pure contextual spike from baseline linguistic smoothness. This flowchart maps the complete EchoPrompt pipeline, a dual-path system designed to filter out that baseline fluency noise. First, the target text combines with an assistant prefix. This restored sequence passes through an instruction model to measure contextual likelihood. Simultaneously, the original text passes through a base model, establishing baseline predictability. Finally, subtracting the baseline creates a pure calibrated difference score of assistant-style compatibility, creating a new metric that ignores shared fluency. This visualization outlines performance scores across the detect RL and real det benchmarks using the Llama 3 8B proxy family. EchoPrompt consistently outranks existing zero-shot methods like IRM and binoculars. It improves over the strongest training-free baseline by significant margins in both AUROC and F1 metrics, maintaining accuracy even on distributionally different datasets like RAID. This chart tracks performance under adversarial conditions. When text is subjected to paraphrase and perturbation attacks, standard detectors experience a sharp drop in accuracy. EchoPrompt maintains a steady high score. Deliberate edits and paraphrasing are designed to hide AI origin by scrambling lexical regularities. Detectors relying on unconditional likelihood or local token entropy lose their signal completely when those specific word sequences are disrupted. EchoPrompt stays resilient because it checks for a structural relationship. Even if an attacker swaps out individual words, the underlying prompt response compatibility remains intact. Detection robustness is achieved by measuring these architectural artifacts rather than easily corrupted token statistics. This graph tracks threshold trajectories across text lengths. For shorter texts with fewer tokens, traditional detectors suffer from drifting decision boundaries, requiring manual recalibration. In contrast, the EchoPrompt threshold line remains nearly flat across all lengths, avoiding erratic shifts seen in other methods. The base model calibration intrinsically controls for sequence length. The difference score isolates the contextual signal uniformly, whether the text is 50 words or 300. The data points to a shift in how we evaluate generative output. We must stop viewing AI text as a fluid, unpredictable mimicry of human writing and recognize it as an output bound to an architectural grid. Instruction tuning engineers a specific behavioral objective into the model. That optimization leaves an indelible statistical mark, separating it from human cognitive patterns. To reliably identify machine-generated text, we must test for its foundational origin. Once a response, always a response.